definition of an odd and an even number. Doesn't that sound so much fun? Do you know what the definition of an even number is? How do you guarantee a number is going to be even? You times it by 2. Right? Is there any number out there you can times by 2 and it's not even? Any integer? So then how do you guarantee a number is going to be odd? Any number theory people out there? Well, what could I do to an even number? If 2n guarantees it's going to be even, what could I then do to guarantee it's going to be odd? There you go. That's the definition of an odd number. It's just an integer. If you double it, it's going to be even. So then if I subtract 1, what does that mean? It's going to be odd. So here what we're saying is we want to make sure theta cannot be odd multiples of pi halves. So when we write that out, it's going to look like this. Theta cannot equal 2n minus 1 pi over 2. Now, that doesn't look very fun, right? But what does that mean? The 2n minus 1 guarantees that we're going to get an odd number here, right? And then it's just going to be odd multiples of pi halves. So I need to add in there where n is any integer. Okay, so I'm going to add that to our list right here. So if we see sine is in the denominator, then we say theta cannot be equal to n pi where n is any integer. If we see cosine is in the denominator, then we're going to say theta cannot equal 2n minus 1 pi over 2. So odd multiples of pi halves. But what if they're both in the denominator? We're going to do one more, and then we're going to get to the good stuff, because you're like, this sucks. And maybe you're right, but let's hang in there with me. What if both sine and cosine are in the denominator? We're just going to do this together real quick. So what if sine and cosine, where are they both equal to 0? Well, you guys have told me about sine. Where does sine start? 0, and then it has multiples of pi where at? We saw it at 0, at pi, 2 pi, 3 pi. So we're seeing those. We're seeing sine is equal to 0 at pi, 2 pi, 3 pi, at those multiples of pi, right? Just barely we graphed cosine. And where did we see cosine was equal to 0? Pi halves, 3 pi halves. So cosine of theta is equal to 0 at those odd multiples of pi halves. So we have pi halves, 3 pi halves, 5 pi halves, etc. If we combine those together, what are we seeing? We're seeing every multiple of pi halves, not just odd multiples, but even multiples. So here's the trick that we're going to do. If we see both sine and cosine in the denominator, then we're going to say theta cannot equal n pi over 2, where n is any integer. And let's add that to our list. And then we can move on to something more exciting. So if we see both, we're going to say theta cannot equal to n pi over 2. Okay. Pause 1 second. What I want you to do is turn to your neighbor and try to summarize what this is saying. Okay? Why are we talking about this? What the whole point of this is. And if you don't know, then we'll go over it in a second. Okay? So try to explain it to your neighbor. Go. Adam, your neighbor, is Hiram. Hiram, your neighbor, is Adam. So you got to turn around and explain it to your neighbor. Okay, whose partner gave a good explanation? Who felt like their partner did a good explanation? I'm going to have them explain it, and they get a high chew. Nobody? You're not going to throw your partner under the bus? All right, Angelina, go. You're going to tell us. What did Allie tell you? Or what did you guys and Allie talk about? We can use any value out there, except if we have sine in the bottom, we can't do those, cosine, and if we see both, do those. All right, thanks for explaining your thoughts. That was almost a good catch. It landed on your desk. I mean, that's good. Okay, so let me show you how this is going to work, okay? That whole thing was just to say, hey, if you're asked to, like, talk about your domain of validity, all you need to do is you're going to look at your denominators and say, well, was sine in the bottom, was cosine in the bottom, or were both? And then you have to put this. So we'll just have that as a side note moving forward. Now we get to get into the fun part, okay? All right. Who here can solve a Rubik's Cube? Is there anyone here who can? No one? I can't. I mean, but I just assumed one of you guys could because you're all so smart. My brother, he could, but he did so by taking it apart and then rearranging it. So, does that count? Or you can take the stickers off too. Okay, so now what we're going to do, guys, when we're talking about trig identities, it's kind of like a Rubik's Cube, okay? Except to start with, it's jumbled up, and what we want to do is organize it to make it look like that. Now, the way we're going to do that is we're going to use our trig identity. So, this side doesn't look like this side, right? But they're actually equal to each other. So what we're going to do, and we're going to do this, instead of just keeping this the same, we're going to kind of change both of them until they match. So what we're doing right here is this kind of process where we're trying to get these to match. Now, kind of like what I said last time, we're going to always start by getting it in terms of sine and cosine. Okay? So I want to put that as a little side note here. We want to get it in terms right as sine and cosine. And to do so, you're going to refer to your things, your identities that we already wrote down. So Brenda, cosecant. How can I think of cosecant as sine or cosine? And that's okay if you peek at your notes. Yeah, 1 over sine. Awesome. Keep going. What about secant? Yeah. And what about cotangent? Are you still with me? It's cosine over sine, because tangent sine over cosine. So we just flip that over. So this is cosine over sine. You guys, are you okay with that? Thanks, Brenda, for your help. So what we've done is we got it in terms of sine and cosine. Now this is where we could actually hit the pause button and say, hey, what do you see in the denominators? And be careful because there's a lot of denominators here. But right here, I see sine, I see cosine, and I see sine again. So if this asks for the domain of validity, and I'm just going to write that as d of v, okay? What would we put if we see both sine and cosine in there? N, or so theta cannot equal n pi over 2, n pi halves, okay? Great. So that's what we just took care of. Now we get to keep going with this, okay? So on the left side, I have a fraction divided by a fraction. What do we do if we have a fraction divided by a fraction? Keep, change, flip. multiplied by the reciprocal. Let's write this out. So when I do, I'm going to keep 1 over sine of theta. We're going to change it from dividing to multiply. And what do we do with the cosine? 1 over cosine? Flip it so it's cosine over 1. And I saw Adam say, oh, because he already saw it, what's going to happen here, guys? When I multiply these straight across, I get cosine over sine is equal to cosine over sine. And once you get the left side to match the right side, you are good. There are some times where people make you actually go through and like get it to say 1 equals to 1. I could have you do that, but we're just going to stop right here. Okay? Unless there's any objections. Anyone want to do? They're like, more work? Sure, let's do it. Okay, no. We'll pause right there. So, with an identity, once you get the left side to match the right side, you're done. If it asks for the domain of validity, you just go back and say, well, what were my denominators? And if you only saw sine, or you only saw cosine, or you see both, you just refer to our chart we filled out and fill that in. Okay? Awesome. Let's try a few of these, and then we'll get to a break point in just a second. But let's look at some of these. Number 3, verify each identity. That means make the left side look like the right side. Give the domain of validity for each of those. All right, so let's get some help going forward on this. Let's go to Peyton. Peyton, what is a good first step? Great, so cosine is good. What about tangent? Awesome. And then on this side we just have sine. Okay, well then that should simplify to give us a true statement. Does anyone see how that simplifies? Go ahead, Peyton. Cosine over cosine is just 1, so then I get that sine is equal to sine. Is that a true statement? So, did we verify this identity? If you get the same thing on the left as you do on the right, then you verified it. Awesome. Great job. Now we do need to say, what is the domain of validity? So I'm going to write under domain of validity. Well, let's look in our denominator. What was the only trig ratio we saw on the bottom? Cosine. So what I'm going to do is I'm going to highlight that real quick. So we saw cosine was in the bottom. If cosine is in the bottom, we don't want that to be 0. Where is cosine equal to 0? At those odd multiples of pi half. So I'm going to say theta cannot equal to 2n minus 1. That's an odd multiple of pi half. Okay, that's it. Wasn't that easy? Now, these do get more challenging if you're like, shh, give me a challenge, Solberg. Just you wait, we'll get there. Ugh. Here's what I want you to do, is I'm going to let you do 4 and 5 on your own. So, follow those same steps, get it in terms of sine and cosine, do a little bit of algebra manipulation, get it to match. And then, domain of validity. Let me give you 2 minutes here. Go. You okay? You need a drink? And when you're done, check with your neighbor and see if they got the same thing you did. Looks like some of you are wrapping up. That's okay if you're not there yet. Hiram, are you done with the first one?
Yeah.
Awesome. And Kelly, you get on the second one? Awesome. Okay, we're going to go through this real quick. Hiram's going to take number 4. So Hiram, walk me through how you did number 4.
So I changed secant to, I changed secant to 1 over cosine. I guess cosine.
Oh, thanks. I'm just right here. Like that?
Yeah.
Okay.
And then I changed tangent to sine over cosine.
Great.
And then you do sine times 1 over cosine equals sine.
Sine of theta over cosine of theta equals sine of theta over cosine of theta. Is that a true statement? Awesome. So then I can highlight it. Great. Now what about the domain of validity?
So since cosine is in the denominator, it means it's the 2n minus 1 pi halves.
So theta cannot be those odd multiples of pi halves. So once again we saw cosine. Nice job, Hiram. Okay, so then let's go to Mikkel for the number 5 here, the second problem here. What did you do here, Mikkel?
Alright, so I did same as 4, simplify secant to 1 over cosine.
Okay, keep on going.
Then we multiply them from cosine theta over cosine theta equals 1, which simplifies to 1.
That a true statement? Sure is. Awesome. What about the domain of validity?
It's same as bin. Theta cannot equal 2n minus 1 pi.
Awesome. You guys are so smart. Do you guys agree? Do you have any questions on that? Okay, cool. I hope you're starting to see it. So this is how we do the basic trig identities. It all just comes down to using sine and cosine. Now we're going to add an element in a second, but first we're going to take a little break.